Now, there's no lone pairs around the carbon. There are lone pairs around the oxygen, but we don't need to worry about that. All we care about right now are the number of the sets of electrons around the atom we're interested in. And it's just because we're not trying to find the shape of the oxygen, we're trying to find the shape of the molecule, and everything is attached to this carbon. So we're looking at how things are attached to the backbone of the molecule. Okay? Now, this is what you need to know. Oh, this is another thing you need to know. Once you've eliminated all the electron pairs, all the electron pairs using this system I've taught you, you should have the correct molecular formula, or the correct molecular shape. So if you've done everything that I'm teaching you, and you've done it step by step, not skipping any space, not skipping anything, you should have the correct molecular shape. Okay? And so that is the correct molecular shape for formaldehyde. Now, earlier in the week, we did some shapes where we had to get rid of electron pairs that were unshared, the lone pairs. And that's how we ended up with the correct shape for water. Okay? When you did your balloon models yesterday, you saw that the two bonds with hydrogen, if your balloon model was done correctly, were at a kind of angle, kind of like this. Here's the oxygen, you were coming off of it like this at that angle. Your balloon model actually showed that. And because when your model is tight, the way I've asked you to do it, then those balloons all tend to push apart from each other, just like our electrons push apart from each other, forming the correct shape for a water molecule. And that's why water has a bent shape. Okay? It's also why formaldehyde has this trigonal planar shape. The name of this is trigonal planar. Both these shapes are trigonal planar. Both these shapes are trigonal planar. Trigonal. Trigonal planar shapes. Trigonal. Okay? This is called an electron pair shape. And once you get rid of all the electron pairs through the system I've taught you, you have a molecular shape. Okay. Any questions about this step-by-step process? Basically what I've done is to take all the stuff we've been learning this week as little separate little things, and we kind of put it together as one long process here. Starting with electron dot notation all the way down to the molecular shape. Okay? This is a different kind of shape for a molecule than showing the shape of the orbitals or the bonds. Okay? It's a different thing than showing the shape of bonds. When we did our balloon models, you were getting a chance to see what the shape of the bonds look like. This is a bond drawing for carbon dioxide. Okay? Let's do a bond drawing for this molecule. Got it yet? All right, good. So starting with our Lewis dot formula here, I'm going to figure out the shape of the bonds. Okay? Again, the central atom, the one that everything is attached to, is the carbon. It's the one we're interested in here. So I'm going to put carbon kind of in the center here. Okay? If you remember yesterday when we were doing our balloons, there's two parts to the double bond going from the carbon to the oxygen. This double bond has two different kinds of bonds. The double bond has two different kinds of bonds. The first bond it has is the one that lies directly on the line between the center of both atoms. And that one we call a sigma bond. The second bond between those two atoms is the pi bond. And the pi bond has two parts. It's kind of like this is the wiener, and what I'm about to draw is the bun that goes around the wiener. And a bun has two parts, right? Okay, top half and a bottom half, at least a hot dog bun does. Okay, so you got a top half here and a bottom half. It's all one bond, just as a hot dog bun is one bun. It has two halves. Well, this bond kind of has two halves. And this is a pi bond. Sorry, someone was asking about those lone pairs on the oxygen. Why weren't we worried about that while I got it? Well, this is where we are worried about it. Okay? If I have drawn my pi bonds so that they're vertical, part of it above, part of it below, those pi bonds, just like your balloon models, are pushing apart from other locations where electrons are located. Okay? They can't be in the same space as the sigma bond because pairs of electrons don't like to be close to each other. That's why we have to have two separate bonds. They have to be in different regions of space. The two lone pairs also want to be as far apart as they can be from these electrons. So the two sets of electrons are going to be in a hybrid orbitals. The two sets of electrons are going to be in hybrid orbitals, one that's swinging out toward you and one that is swinging back away from the paper. Okay? So these are two sp2 hybrid orbitals. Where the lone pairs of electrons are located. One of them here, one of them here. Okay? Okay. The two shared electrons going to the hydrogens, then those are sigma bonds. Okay, just like this is a sigma bond. Anytime you have a bond, you kind of have a covalent bond, shared set of electrons. You always have to have a sigma bond. You can have a pi bond in addition to that, but you have to have a sigma bond. So one of them, the blue one I have here, is swinging out toward you, and the orange one is swinging back away, just like this blue orbital here is swinging out toward you, and the orange one swinging back behind.